So we're going to cover the Python notebook, Jupyter notebook that accompanies the textbook mining complex networks is shown here. More specifically, we're going to be covering chapter 1 today. Here's a link to the GitHub repository where you can find all the notebooks. So at the time of recording, we are working on a second edition for the textbook. So the most recent versions for the notebooks can be found in Python notebook second subdirectory. When the second edition is ready, those are gonna go into the Python notebook directory. There are also other things on the repo, so some Julia notebooks, information on how to build your Python environment using Conda, but you can use other methods if you're familiar with other ways. There's information about which packages are going to be used and what data set we're going to be using with the proper references. So for chapter 1, we're going to be, chapter 1 in the textbook covers some basic graph theory concepts, and we're going to be applying some of those concepts to two real networks. So I assume that you're familiar with Jupyter Notebook and how to run the different cells in Jupyter Notebook. Also that you're familiar with some Python packages, common Python packages like NumPy and Pandas. For manipulating the graphs, we're going to be mainly using the iGraph package. So this we're going to cover into a little more details as you may not be as familiar with this package. So let's run the first couple of cells. This is basically pointing to the proper directory where to find the datasets and importing the proper packages. So what are we going to do in this notebook? Well, we're going to look at simple graph statistics, some things like degree distribution, clustering coefficient, shortest path distribution, and we're going to be doing so for two different graphs. One is more of a kind of a social type graph, which are linked between GitHub developers, while the other one is a physical network, namely a power grid. And the main take-home message in this notebook, in this first chapter, is the importance of doing exploratory data analysis, EDA, when you're doing any kind of data science experiment, data science analysis of data sets. So the importance of understanding your data. One thing to note is that we're going to be using the term vertex and node interchangeably. iGraph uses vertex, but we often talk about nodes and edges. So the first graph is this GitHub developer graph, and some details about it is given here. But for the sake of what we're going to do, the important thing is that the nodes are the GitHub developers, and the edges correspond to some mutual follower relationship between two developers. The vertices have some features or attributes, and the ones we're going to be using are the fact that there are two types of nodes, two types of developers, namely the web developers and machine learning developers. Okay, so let's read the data set and construct our first iGraph graph. Okay, so what we've done here is that we've read the data in a data frame using pandas, and then we built the iGraph graph object using this graph tuple function, where we basically pass it a list of tuples where each tuple is an edge. Okay, so let's look into a little more details. So the data we read in a data frame corresponds to basically edges, and the edges contains the vertex ID for the first vertex and the vertex ID for the second vertex that makes up each edge. So the first edge is between like ID 0 and ID 23977. The second edge between ID 1 and ID 34526, etc., etc. And then using that, we built our GitHub graph, which is an iGraph graph object. Two things that are very important in iGraph object are what we know as the vertex sequence. So VS is a vertex sequence, and basically it's a sequence of vertices, as the name indicates, and the first object corresponds to the first vertex, vertex 0, which has ID 0. The second object is the second vertex that was read in, vertex, so it's one zero based, so 1 corresponds to the second vertex, and it has ID 23977. This is because it's stored in the order that the data is read in. So the first edge that was read in is 0 to 23977, so our first two vertices, 0 and 1, correspond to IDs 0 and 23977. So as you might guess, the next one is ID equals to 1, and then we have the next one would have ID equals to 23526, which is this one, etc., etc. Okay, so this notion of vertex sequence is important, but beware not to confuse this ID or name and the actual sequence of vertices. Everything that is found inside the curly brackets are what we call attributes. By default, iGraph is going to give a name attribute, but we kind of change it to call it ID because that's how it's referred to in this data set. You can call it whichever way, whichever name you want. The other important things to know in iGraph is this notion of edge sequence. So same way you have a sequence of vertices, you have a sequence of edges. And in our case, the first edge is edge 0. There's no attribute yet, but by default, you always have the source vertex, which is vertex 0, and the target vertex, which is vertex 1. Okay. So let's add some node attributes. We're going to read in this other data set that is stored in this file, this CSV file, into a data frame. So this data frame is going to have the first column, which is the vertex ID. We already read the vertex ID in the previous cells. And the two attributes we're going to add are names, and ML target is a binary indicator. It's 0 if the actual user or developer is a web developer, and it's equal to 1 if the developer is a machine learning developer. Okay, so we can build dictionaries, and in this case, what we do is that we're basically building a dictionary that maps the vertex ID and the name, for example, or the binary indicator if it's an ML developer or not. So the first two are web developer, then this vertex is an ML developer, etc., etc. Okay, so let me get rid of that. And this is how one way you can add attributes to the graph. So I'm going to call the vertex sequence. I'm going to create a new attribute which I'm going to call name, and to that I'm going to map the name that correspond to the different IDs. And I'm going to be doing the same with another attribute which I'm going to call class, and the class is going to be called either web or ML depending on the value of this ML label that we saw, which is 0 or 1. So 0 is going to map to web and 1 is going to map to ML. Okay. So let's look at, for example, our first vertex. So the first vertex has ID 0. It has this name here, and its class is web because the ML target value is equal to 0. Okay. We can build subgraph because we have two types of developers. So I can get all the vertices where the class is equal to ML, build a list out of that, and pass it to the .subgraph function. And that's going to build a subgraph of this GitHub graph that contains only the ML developer. And I can do the same with the web developers. So that's going to create two subgraphs. And in here, I'm introducing a new feature in iGraph, which is this .vcount. This is vertex count, how many vertices or how many nodes there are in the different graphs. So let's run this. So we've built our two subgraph. The whole GitHub graph contains 37,700 vertices or nodes. The ML developer contains 9,739, and the web developer graph contains 27,961 vertices. Okay. One interesting thing to notice, and those are the kind of things that are important to know if you do some analysis, sometimes when you're looking at a graph, having nodes that are disconnected could be a problem. So in this case, some of the ML developers are connected only to web developers and vice versa. So when we build a subgraph, some of the nodes in the subgraph are going to have degree zero or are going to be disconnected from the graph. So let's look at that. I mean, this is the long way. This is not how you would do it, but let's do it the long way to see exactly what's going on. So I'm going to build a counter here that's going to count how many ML nodes only have neighbors or are only connected to web developers and how many web developers are only connected to ML developers. So I'm going through all vertices. If the vertex class is ML, then I'm going to look at its neighbors and I'm going to look at the class of its neighbors for all of them, put that in a list, and then map that into a set. And if if the list contains only web developers, then the set is going to be equal to this unique element set with only the web label. In which case I'm going to add one to my counter. I found a node that is an ML developer that only has neighbors that are of the web developer type. And the same thing for if the class is equal to web developer, I'm looking for cases where all the neighbors are of the class ML. And if it's so, I add one to the counter and then I print, what are the counter. So in this case, this is telling me that 2,308 ML developers are only connected to web developers, and 285 web developers are only connected to ML developers. Okay. Well, of course, there's a much easier way to do that. And the way you would do it is, okay, let me look at the degrees. So let's introduce this dot degree. Dot degree here, if I don't put anything in the parenthesis, is going to be give me the list of degrees of all the nodes in the graph. So I can do that for the entire graph. I can do that for the ML subgraph and for the web subgraph. And I can count how many of those are equal to zero. So for the entire graph, there are no nodes that have degree zero, so everything has at least one connection. But in the ML subgraph, as we saw earlier, there are some 2,308 that now have degree zero because all of their connections were to web developers, and the same in the web subgraph, 285 have degree zero because all of their connections were to ML developers. So the other graph we're going to be looking at is quite different, actually. It's a electric grid network. So details can be found in this link in this website. But essentially, it's you have a node would correspond to different types of location in the grid and they have different types: joint, merge, plant, station, substation, etc., etc. And there's an edge if there's actually a physical link, a physical connection between two, plant, two stations, merge, join, etc. So two physical locations. So we're going to be reading the graph. And I'm going to use a different method here. I'm going to use an iGraph function called read and call. So it's going to read data that is represented as different columns. So those are my edges. The graph itself is directed. So for example, you have an A-B edge, which means from A to B, and you can have a B-A edge from B to A. But we're going to cast it into an undirected graph. And for that reason, I could end up having multiple edges. For example, if I have an AB and a BA edge, well, I will in my undirected graph, I would have two edges, which I will simplify by calling this dot simplify function in iGraph so that I get only one edge at most between any two locations. Okay, so we have our graph. The same way we did with the other graph, we're going to read in attributes in a data frame. So in this case, the attribute correspond to, for a given vertex ID, we have a longitude and a latitude. This is a physical location, and the type of node that we have, a joint, a substation, etc., etc. We're going to build dictionaries the same way we did the previous data set, so a dictionary for the longitude, the latitude, and the type of node, and we're going to store those in the iGraph object. So we're going to store the first thing to notice here, yeah, that's an interesting point that we're going to look at. So in the grid graph, if we look at the vertex sequence, the names are stored as strings. It's going to be convenient to use integers because in our attribute data frame, the vertex ID are actually stored as integers. So the first thing I'm going to create here is an ID attribute, which is just the integer version of the vertex names. That's it. That's all it is. And then I'm going to use this to build the longitude, the latitude, and the type attributes inside my graph. So if I do that, now I have, for example, my first vertex contains the name. The ID is the same as the name, but as an integer, the longitude, the latitude, and the type of node that we have. Okay, so we can do some simple counts here. For example, this function counter is an interesting function in Python. What I'm doing here is that I'm looking at all the types of nodes and I'm passing it to this counter function and returning the most common. So you can see the most common type of node is a join, then a substation, a merge, a station, etc., etc. I can also look at longitude and latitude and take the min and the max values, which gives me the range of longitude and latitude that this data set is covering. And we can plot the data. In this case, it's going to actually mean something. You should recognize what we're going to see. So I'm going to add an attribute which is a vertex size of 4. I'm going to basically build a dictionary of colors, and I'm going to map the different types of nodes to different colors. So the vertex color is going to be this dictionary value depending on the type of vertex. The edges are going to be gray. And for the layout, I'm actually going to use the longitude and latitude. I need to reverse the latitude because otherwise the plot would be kind of upside down. And then I'm passing that to the plot function of iGraph. So that's the layout that we're going to be using. So longitude, latitude, and this bounding box essentially represent the size of the plot we're going to get. So let's see what this looks like. I guess we recognize the map of Europe, and the different colors correspond to the different types of nodes. So we have our two graphs loaded in. In the case of the developers, we also have two subgraphs, but we have our two main graphs loaded in, which are the GitHub graph and the grid network. And yeah, we also have the two subgraphs. So in the what we're going to do now is to compute some basic features, and those are the ones that are found in the textbook. So to do that, I'm going to define a function here that takes as an input a given iGraph object that computes and returns a bunch of different statistics describing this graph. So to run that for the 4 graphs that we have takes about a minute or so. So I'm going to launch it, and then we're going to go while this is running. This is what is running right now. So I'm going to go through what we're computing here. So this g.degree will compute a list of all the node degrees in the same order as the vertex sequence. This is vcount is the number of vertices, ecount the number of edges. Then for the degree sequence, I'm going to return the minimum, the mean, the median, the 99th percentile, and the maximum. So this gives you an idea of the degree distribution. Also going to compute the diameter. Diameter is the length of the longest path between the longest shortest path, if you want, between two nodes, right? So the length of the longest shortest path between two nodes in any connected component of the graph. And then I'm going to look at the different connected components. Dot membership indicates that which node belongs to which component. So this is 0 based. If I take the maximum value plus 1, that tells me how many connected components there are in that particular graph. I can look at, for each connected component, I can look at the giant component. For each graph, sorry, I can look at the giant component and see how many vertices there are. I can also look at how many nodes have degree 0. And we're going to remember for the subgraph, the ML and the web subgraph, we know there's going to be some nodes with degree 0 because we already did that analysis. And the last two statistics we're going to compute are the clustering coefficient or transitivity. So the first one is the global clustering coefficient, and it's called transitivity undirected in iGraph. And the second one is the average local clustering coefficient or average local transitivity. Mode equal nan just means that if I have a node that has fewer than two neighbors, then of course I cannot compute the clustering coefficient because there can be no triangle. So either you will assign the nan value, which means not a number, or you assign, the other possible mode is 0, where you assign value 0. Okay, so the computation is done. We've computed a list of lists because this particular function returns a list. So now we have a list of lists with all of our statistics, which we're going to store in a data frame because it's kind of easier to look at and display the data frame. So what we have are the four networks, and for each of them we have all the statistics that we've computed. To use this math kind of notation and all of that, you can look here how it is done. For example, this is how to use like LaTeX-like notation to represent some mathematical objects in Python or in pandas in this case. Okay, so this gives us how many nodes and edges there are in each of our graph. The smallest degree, so notice we have degree 0 here for our two subgraph, the ML and the web subgraph. The mean degree, the median degree, the 99th percentile, the maximum degree. And one thing we notice right away is that for the developer, the GitHub developers, the degree values vary quite a lot, from like 0 or 1 to some potentially very large number, almost 10,000. For the grid, it goes from 1 to at most 16 with a median of 2, so much lower degree. If we look at the diameter, there's a drastic difference here, like 9, 11, 13 for our GitHub developer graphs or subgraphs, but 147 for the grid graph. The number of connected components, there's a single connected component for the GitHub graph, but if we look at the ML and the web subgraph, then there are disconnected components, and there are also 59. So there are disconnected components also in the grid subgraph. This is the size of the largest component and the number of isolated nodes or nodes with degree 0. We already computed those values earlier. We also computed the global and average local clustering coefficient. So notice here that the global clustering coefficients are relatively low, a bit higher for the grid, but relatively low for the web subgraph, while the average local clustering coefficient is somewhat higher for the developer graph and subgraph. So why is this so? Well, remember the difference between the global and the local, right? If we take the global clustering coefficient, we're considering all possible wedges in the graph, and then how many of those end up being triangles. But if we take the average local, then we're computing this locally for each node and then taking the average. So for example, if you have a node with very, very high degree that has a lot of neighbors, then it can contribute quite a lot to the global clustering coefficient, but it's only one value in the local clustering coefficient. And it turns out in this case, if we look at the distribution of degree versus the local clustering coefficient, the nodes with very, very high degree actually have very small local clustering coefficient. So that explains this discrepancy between the two values. And you can see how I did the plotting here. So basically I built on my x-axis, all of the values for the degree of I used the subgraph of the ML developers in this case, and I only considered cases where the degree was strictly greater than 1 because I want to have the possibility of having triangles. And then for all of those, I computed the transitivity, so the local transitivity. And of course, I only consider the one that is not an NaN, or not a number. Those are the ones that correspond to the nodes that have degree 2 or more, and basically plot X and Y in the usual way using Matplotlib. So the next couple of cells are really more visualization that we used for the book. So basically what we're doing here is that we're selecting a subset of the vertices for the grid network, basically corresponding to the Iberic Peninsula, so Spain and Portugal. So we have a range here for the latitude and the longitude. We build a subgraph using the vertices that fall into this subset, if you want, and then just pass it to the plot function. So that gives us, familiar plot where you see, the concentration in probably near Madrid and Barcelona and what have you. So you can recognize the shape. And we can do the same for the GitHub, in this case, the GitHub ML subgraph. In order to, this graph does not have any particular physical layout, so we're going to use the layout provided by iGraph directly. So layout underscore auto is going to map to one of the what is the most appropriate given the data set that you pass. And then we're going to look at a region of, because this is quite a big thing to plot, and in particular for the textbook, we didn't want to have something too big so that it could be readable. So we're going to build a graph by gradually increasing some kind of rectangle, so that physical rectangle for the layout until we get about 800 nodes. Okay, so that's all it is. And it's just a way to, it takes like a few seconds, and it's a method to plot. It's a way to look at, sorry, a subset of our graph. And you can see this is quite different. I mean, there's no particular organization here. And you can see there are some hubs that seem to have very, very high degree or very high concentration of nodes. And there are some nodes that are very low degree and a bit more peripheral. Okay, so now we're going to go back to some of the statistics that we computed earlier and do it maybe a bit more in a bit more details. So look at important statistics for the different graphs, and in particular compare the GitHub developer and the grid networks and see that there are very, very noticeable differences, even using simple things like degree distribution, for example. So what I'm going to do here is that I'm going to get all of the degrees for the GitHub graph. I'm going to build the CDF, so the empirical cumulative distribution function, given this list of degree, and basically uh, plot it into in a what we call a semi-log plot. That means that my x-axis is going for the x-axis we're going to use a logarithmic representation, and you're going to see why we do that. It's because the values are pretty big in this case. Remember, the degree can go all the way to almost 10,000. So this is my empirical cumulative distribution function for the GitHub developer graph. So what this means is that, for example, if I look at degree 10, I have, about 60 or just above 60% of my nodes that have degree 10 or less. But in order to cover all of my vertices, I need to go to degree, almost close to 100, and there are a few nodes that have extremely high degree up to about or just under 10,000. If I do the same thing for the grid network, you can see now, and I've done the semi-log x plot again, and in this case, the maximum degree, if I remember, is about what 16, I think. So you can see that most of the vertices have very low degree. Actually, this is degree 1, degree 2, by degree 3 or 4, we've covered almost all of our vertices. Another thing we can look at is shortest path distribution. So starting from a given vertex, how many hops do I need to reach every other node, for example? This can take quite a lot of time to compute, so we're going to do something here. Let me go through the details. So for the GitHub graph, I'm going to look at the giant component, and we're going to take a random selection of 100 nodes, okay, or vertices without replacement, so 100 distinct vertices. And for each of those, I'm going to use this distance function with those vertices as sources to compute the distance to every other vertex in the graph. So doing the all-to-all computation, you can try, but it's going to take quite a long time because remember, this is kind of n square type of computations or O of n square computations that you need to do. So we're going to do all of those computations and map that to, or use the counter function to, and then sort them and pass this to a bar plot. So what this is doing basically is to count, okay, in my sample of 100 nodes, I computed the distance to every other node in the graph. I dropped the one that had zero distance, which is basically the distance to myself. Okay, so I didn't want to have zero distance. And you can see the distribution here. So how many path length of size 1, 2, 3, 4, 5, 6, etc., etc. So you can see that for most pairs, you don't need that many hops to go from one node to the other, right? This is an illustration of this, so-called 6 degree of separation experiment that you may have heard of from a while ago. But this is an example. This is something that you see often in like social network type of graphs where the diameter is relatively low and the size of shortest path to go between node A and node B is usually quite small. This is computing exactly the same thing for the power grid network, and you can see now it's quite different, right? I mean, it goes all the way to about almost 140 hops, and if I take, a random pair of vertices, a random sample with two nodes in my grid, it could take, 40, 50, 60 hops to go from one to the other. And this is, of course, because of the very nature of this power grid. I mean, it's a geographical and physical network. So that's a quite different structure than we have for a more social type network. And the last thing we're going to look at is the local clustering coefficient, and we're going to verify the known fact that very often the distribution of the clustering coefficient, local clustering coefficient, and degree follows what we call a power law relation. Okay, so let's do that. We're building a data frame here that will contain the local transitivity or local clustering coefficient for all of the vertices. And I'm using mode 0 here, so I'm going to have a value of 0 for cases where if there is a node with degree, less than 2, but it's not going to matter because I'm not going to look at nodes with degree, with very small degree. So I'm storing all of those in a data frame where I have one column that has the clustering coefficient and the other column has the degree. And then I'm going to filter my data frame to only keep the nodes with degree between 10 and 1000. Let's see what we get. So we have a data frame here that has for degree 10, I have this clustering coefficient, degree 11, etc., etc. One thing that I've done is that I've used, if you're not familiar with this group by, I've basically grouped all of the nodes with respect to their degree and took the mean value for the clustering coefficient. That's what this syntax means. Okay, so if you're not familiar, you can look at any good introduction to pandas, and those are very useful function provided by the pandas package. Okay, so given that we can do two things, we can plot. So we're going to actually plot these values, but we're also going to fit a regression line on the log-log scale. So if I take the log of the index value of my data frame, which are the degree, and the log of the clustering coefficient, and I'm going to fit a linear regression model, and then I'm going to plot this line along with the data itself. And this is what I get. The slope here gives me an estimation of the power law exponent relationship, and you can see, and for the most part, this power law relation between the log of the, so between the degree and the local clustering coefficient.